In other words, when you add reactions together, you add the enthalpies of reaction. Remember that? And when I do equilibrium, I'm going to do an extension of that. So let me just get back here. Here's the problem. He gave you 3 equations. He asked you to calculate the equilibrium constant for this equation. And we know from Hess's law we should be able to add these up in some fashion to get this equation. And for those of you who may have didn't take me when I did Chem 1A, I said there's a simple way of doing it. And the textbook does the long, involved way where he keeps writing equations and rewriting equations. Okay? And I said, we want to look for a unique substance. Could be molecules or ions. In this case, it's all molecular. So we want to look for unique molecules. I have water here. I have water here. That's not too unique. Okay. In fact, I have a situation, let's see, maybe, yeah, okay. So I have water in 3 of these equations. That's not a unique molecule, so I'm not going to start with that. I have H2SO4 here. Here's H2SO4. No H2SO4, no H2SO4. So that means if I want H2SO4 on the left, I have to add 1 times this equation. Okay. If I look at the next thing, this is H2S, no H2S, no H2S. H2S is on the opposite side, so I put a minus sign here. The effect of the minus sign is it puts minus, minus, minus for all of these things. You reverse it, now you have H2S on the other side with everything with a positive sign. So far, so good. Do I have to use this one? Well, I must have to use it because this has H2O liquid, H2O gas. This has H2O liquid. This one has no H2O. So if I look at this one, I have plus 1 H2O on the right. If I add this equation, I'll have 1 H2O on the left. Still cancel out. And sure enough, here I have minus H2O because I multiplied by minus 1 plus H2O. They're both liquids. They cancel out. So I got rid of my H2O. So that's the set of multipliers that will allow me to combine those 3 equations to get the equation of interest. When we did delta H, in other words, last semester we did Hess's law. And I'll just call this delta H4. I'll call this K sub 4. I'll call this K1, K2, K3. So when we did enthalpies, we just said we do the algebraic summation. And this multiplier was plus 1 times, oops, I got right, delta H1, plus, and here, using the parentheses, it really means you're subtracting delta H2. In other words, all I'm doing is putting in the multipliers times each of the enthalpies. And this one is plus, and the multiplier is plus 1 times H3. If I want to do the equilibrium constants, what do I do? I use these multipliers as exponents for the k's. That's because the equilibrium constant is related to the thermodynamic properties by a logarithmic term. So if you have a log or a natural log k, it becomes log k to the a. So when I'm adding enthalpies or free energies or whatever else, we'll do all of this again when we get to thermodynamics. If these were the thermodynamic properties, I would just put the multipliers in, but when I'm talking about equilibriums, they go into the term as an exponent because of the properties of logarithms. Okay? So I'm just saying it's k1 to the plus 1 times k2, what's the multiplier? Minus 1 times k3 to the plus 1. This is sort of trivial because all you're doing is multiplying and dividing by the k's. Nothing exciting. Let's see if I can find a more exciting one. But this is the general rule. You're multiplying the k's together, and you're putting some of the numerator, some of the denominator. Now I can justify this. I gave you the rule. That's all you need to know to do problems. But let's write the equilibrium pressure expression for this one. I'm going to say O2 squared H2S, first part. What's in the denominator? One, because it's H2SO4 liquid. We don't put liquids into the equilibrium expression. So that's what my equilibrium expression looks for the final reaction. I mean, this is the final reaction. That's the one you're solving for. The equilibrium expression for this one says concentration of SO3, concentration of H2O because it's a gas, to the first part. That's a liquid again, so it doesn't appear there. I'm going to, when I say minus 1, I'll reverse the equation. I'll write H2O liquid. Well, mentally, can you reverse that? Good. So what's on the product side here will be on the reactant side. So the equilibrium expression for that is going to have SO3 in the denominator. Because remember, if I reverse it, this is the reactant side. Reactant's going in the denominator. H2O liquid doesn't go in. On the product side, I'd have oops. H2S is what I want to write eventually. Concentration of O2 squared. Okay. And this one, what am I going to write for the equilibrium expression? This is liquid, so it's 1 over, this is the gas, like that. So I look at all of this, the H2O's go out. What else goes out? SO3. And what do I have left? H2S times oxygen squared. What did I write for this one? H2S times oxygen squared. Okay. So if I put in the number for this, the reciprocal of the number for this, which is what it says when you say K2 to the minus 1, it means you're dividing by it. But how will you do this on your calculator? Parentheses, enter this number, caret plus 1. Parentheses, this is the times in here. K2, the number goes in here, caret minus 1. Now you push equal and it does all the algebra for you. I didn't finish writing it to get the idea. Because I wanted to get to a more interesting equation. I know.
I didn't give you a challenging one on the quiz either. Darn. I thought I had a better one on the quiz. Well, let me go back to that homework set.